In this video, we will see the topic solution of difference equation using Z transform. In previous videos, we seen how to use the Z transform for the analysis of the discrete time system. So for that purpose, we use the Z transform formula to convert the given time domain system into Z domain. Then with the help of pole zero plot, we'll try to analyze the system for its stability. Then with the help of ROC, we will try to see the causal, non-causal and anti-causal systems. Now here this equation number 1 is given is an differential equation in terms of discrete domain, where y of n is the output response, y of n minus 1 and n minus 2 are the previous output response, and x of n minus 1 is the input response. Now how to find out the solution for this Z transform? So for that purpose, actually our main aim is to find out the analysis the system transfer function, and system transfer function is denoted by h of z, which is y of z upon x of z. So our main aim is to find out the h of z. So for that purpose, first of all, convert this given equation into Z transform. So here y of n Z transform of y of z. Here we'll write z raised to minus 1 y of z. Here we are using time shifting property. So time shifting property tell us that n minus 1 is the delay. So say here z raised to minus 1 y of z plus 4 z raised to minus 2 y of z is equal to x of z, z raised to minus 1 x of z. Okay, then here in place of x of n minus 1, here only x of z is given, so that's why here x of z. So we have to find out y of z, which is y of z upon x of z. So club the terms which is related to y of z and then do the cross multiplication. So we will get here 1 upon 1 minus. So now here we want an positive powers of z, so divide and multiplied by the z raised to minus 2, because maximum negative power is the z raised to minus 2. So by dividing and multiplying z raised to square, we will get the positive powers. Okay, so by that we are in position to find out the h of z. So now here we have to find out the inverse Z transform of h of z, means we have to find out the impulse response h of n. So h of n, so to find out the inverse Z transform, what we are doing here, z square here, so we are saying h of z by z. So what will get z upon z minus 2 square. So this is the Fourier inverse Fourier transform of n into 2 raised to n. Already we seen the Z transform, because here repetitive root, so that's why n into 2 raised to n. Okay, so with the help of differential equation in Z domain, we are in position to find out the impulse response, that is the impulse system response in time domain. Now next question is find the transfer function and the unit sample response of the reference equation. So again here what we'll do, again here we converted the given discrete signal into Z domain, and we'll find out here the Z transform transfer function h of z. Okay, and then h of n is the inverse Z transform of this, that is a 0.25 raised to n into un. Okay, next numeric is given the transform function. Okay, now these are the applications of Z transform and inverse Z transform. Okay, so with the help of this already we discussed, we can analyze the discrete systems. Then this Z transform mainly used for the digital filter design, that is IIR and FIR. Okay, now we will see some more numerics. Now see, this is the very interesting numeric pole zero pattern, and means plot the pole zero pattern and determine which of the following system are stable. So here for this given differential equation, we have to plot the pole zero plot, and based on the pole zero plot we have to comment about the stability. So what is the first step? Convert this given discrete differential equation into Z domain by taking the Z transform. Then club the term related to yz and cross multiply, by which we will get yz upon x of z. Then here we'll use the we'll try to find out here the complex conjugate roots. Okay, so with the help of this complex conjugate roots, now the numerator part gives us the zeros, so equate it to equal to 0, that is z is equal to 0 and z is equal to -1. Poles are equated equal to 0, that is 0.5 plus j. Okay, now these poles are combination of real and imaginary part, so because of that, here see, this is the pole we plot 0.5, okay, plus 0.5, so this is the first pole. Okay, 0.5 plus j 0.5, see this upper part 0.5 plus j 0.5. In the same way, the next pole is 0.5 minus j 0.5, so 0.5 minus j, so at the lower part of the imaginary axis because of minus j 0.5, and at center z is equal to 0 and here z is equal to -1 is the zeros. So all these poles, because of 0.5, these poles are inside the unit circle, hence this system is the stable. See here, hence this system is the table. Okay, in the second numeric is also in the same way. Differential equation is given. First of all, find out the y of z, then simplify this equation, take the roots. With the help of these roots, we are in position to find out the zeros and poles and plot these zeros and poles on unit circle. In this numeric, the pole 1.2 is the outside the unit circle, hence the system is the unstable. Okay, so some practice problems are given, so try to solve this problem similar to the previous one. Now this is the next pattern. See, find the unit impulse response and step response for the following system. Means we have to find out the unit impulse signal means which one, delta, and step means u of n. So we have to find out the, means this is the inputs are, two inputs are given. First input is the unit impulse response and second input is the step response. So this is the differential equation given. In this, x of n is given, okay, that is unit impulse and step response. So again, take the z transform on both sides, then find out y of z upon x of z. Now first thing what we have to find out, we have to find out impulse response, that is in case of this, now x of n is delta n and delta n z transform is x of z is equal to 1. So see here, y of z upon 1, okay, then convert these negative powers into positive powers, find out the roots, so by which then use the partial fraction. Using the partial fraction, we'll find out a is equal to 2 and b is equal to -1. So then this z we taken on this side, so because of this we can find out the inverse z transform, that is a 2 into half raised to n u of n minus 1 upon 4 raised to n. So this is what unit impulse response. We find out the unit impulse response, that is y of n, in discrete domain by taking the inverse z transform. In second step, now x of n is, we have to treat it as a step response. So x of n is equal to u of n, and we know the u of n z transform is z upon z minus 1. So here y of z, here in place of x of z we have to substitute what, z upon z minus 1. So we'll take on this side, so we'll get z upon z minus 1. Simplify this again, use the partial fraction to come up with the inverse z transform. So we will get this is the taking inverse after solving partial fraction, taking inverse z transform, we will get what, the here this unit impulse response in discrete domain. Okay, the next numeric is the same. Okay, go through it. All the numerics are solved in detail. Okay, same here, this numeric is also same. We'll find out the impulse response. Okay, so impulse, when you want to see the question, when what is the question here, determine the impulse response h of n. So impulse response h of n we have to find out, means this differential equation, convert it into z transform, by that we are getting h of z, and impulse response h of n means take the inverse z transform of h of z, which is nothing but the impulse response. Okay, and in the above numeric we'll try to find out unit impulse response and step response for the given differential equation. See here, unit impulse response, in that case we have to find out y of n. Okay, and when we are finding out y of n, what we are considering, given x of n, is either, see here, we'll find out y of n. In that case, we consider x of n is equal to delta n when unit impulse response. So because of that, this is the y of n by taking the inverse Z transform. When we consider step response, that is the x of n is equal to u of n. So we'll find out the output response when input is equal to unit step response. So this kind of two numerics patterns are coming in case of the differential equation. Okay, so go through this numeric. Some other numerics are also mentioned here. See here, a causal system is represented by the following difference equation. Already it is mentioned, it is a causal system. So again convert this differential equation into Z transform. Okay, then come up with the h of z. So it's a causal system. Okay, so because of that, this ROC is z is greater than 1 by 4. Part B, this is we find out only the system response, that is h of z. Part B, find out the unit impulse response. So because of that, x of n we treated as a delta n. So x of z is equal to 1. So because of that, y of z is, we find out, take the inverse Z transform. Okay, so we'll get here, this is what unit impulse response. Okay, and the poles are what, 1 by 4, which is inside the unit circle. Hence the system is the stable as well as the causal. Okay, so I request all of you, please try to solve the numerics which is given in the notes, and try to do the practice of solution of differential equation, where we'll try to find out impulse response in discrete domain, then we'll find out unit impulse response, then step response by using Z transform and inverse Z transform. Thank you.